Q&A! Q&A day. Ding! Carly Page from Martin Marietta Materials, Colorado. She works as a quality control for the ready mix outfit. John, is there any chance you know Carly? You meet Carly?
I have not met Carly.
Nice.
Heard about Carly,
Great
but
person
not
in the
met
industry.
Carly.
Works with McCombs and the rest of the crew over there. John, is there any chance you could do a video on the mechanism of ASR mitigation using Class F fly ash or similar SCMs, supplementary cementitious materials? Sorry, I'm gonna sneeze.
It's a question I've gotten many times in training, and it's difficult to find a solid answer online, but it's something we deal with every day. Thank you so much for the question, Carly. That is a great one. Yes, we can.
Yeah, we can answer the question. And Carly, there's a lot of references out there for you to use. My entire PhD dissertation was on the impact of nanosilica size and surface area on the mitigation of alkali-silica reactivity in concrete. That being said, when you look at the title, the mitigation of, for some reason, was left out.
Oh.
You didn't notice that? Wow, somebody paid attention. Anyway, so in that, I think it's chapter, the reason why I'm looking at Whitney's, she helped me write this. Like, my PhD, Whitney helped me a lot. She was the main editor. Love you. So anyway, I believe it's chapter...
I want to say 3, but I don't.
Chapter 1, 2, or 3, it goes into the mechanisms of ASR. I believe that a definition of ASR and what the mechanisms are all about is warranted. And there are some better authors out there that I refer to.
Right.
Ichikawa is one of them.
Land.
Land doesn't talk about ASR.
Oh, it doesn't?
Garcia et al. And these were papers back in 2011, 2009. Katie Bardaget and her group over at the Denver Federal Center of the Bureau of Reclamation, they had a paper published back in 2009 where they talked about how ASR was getting worse because of Class F fly ash changing, and then the aggregate that we're using is different. But you know, your specific question was, how does Class F fly ash
or SCMs?
Or SCMs enhance the concrete. And when I first started working at Lafarge and I was getting into ASR, I was educated on that the F ashes that we were using were used to reduce the sodium equivalent content of the binding component for our concrete, right? And there were some cases where, man, my nose. There were some cases where we would use a fly ash and actually get an increase in our sodium equivalent content. And
yeah, we've worked with a couple that just
totally
a nightmare, and they still make the spec.
Right. Well,
it's another video.
That's another video. So, so the question is, if we do, let's say we do have a Class F fly ash, I might have to go off camera to sneeze again. But if we do go above that sodium equivalent content, and we're putting more in there, what is that Class F fly ash doing for our concrete? I'm going to go off camera. You give your 2 cents.
So I know with the supplementary cementitious materials, you're getting more efficiency.
Which Class F fly ash is.
Right, I know, but well, like your manufactured ones. Okay, so theoretically, your SCMs. You're getting more efficiency, generally, if you have a good one, out of your cement particles. So it should be creating a denser, more durable concrete that is less susceptible to ASR and other chemical and physical attack. Basically, the goal is to create a better concrete, so you don't have to worry about any of that stuff impacting your concrete as much as it would be if you didn't have it in there. So yeah, I mean, ideally, that's what you're trying to do, is just it does help to increase the resistance to ASR, but it's just should be creating a better, longer lasting concrete in general. No, you're great.
I just took some allergy stuff.
Yeah.
Hi. Sorry. Good job.
Thank you.
I agree with her. I'm going to break it up into a few mechanisms.
Sure.
Can I do that?
Please.
First and foremost, I want to make an assumption that the Class F fly ash that we're talking about is not the dirty, nasty.
It's like the good stuff.
Beige, maybe a little bit light gray.
Yeah.
Ball bearings with a 40% to 70% silica content.
Yeah.
Low
carbon content.
Low carbon content. Low like ammonia smell. No ammonia
Right.
smell. So they're really good. Like the Class F fly ash from 1998 to 2002. Just like really good stuff.
Yeah.
So that's the initial assumption. And here in the state of Colorado, we normally use 20% replacement.
Right.
Of our Portland cement with our Class F fly ash. So we have a pozzolanic material replacing a hydraulic material. So I want to separate the mechanisms. First and foremost, with the pozzolanic material, we're assuming that it's a good pozzolanic material, we're going to induce some of that pozzolanic reaction to consume the calcium hydroxide to turn into the calcium silicate hydrate. So this is our aggregate, right? In our aggregate, we have to assume has a very reactive silica tetrahedron to it, or a very reactive silica that is susceptible to what we call alkali silica reactivity and some wonderful tests. So when we put our aggregate into our hydrated cement matrix, there are 3 things that we have to worry about, 4 things really. The first thing is that reactive silica at the surface of the aggregate. The second is that dead open space between the reactive aggregate and the
cement particles.
the hydrated
cement matrix.
the hydrated cement matrix. So that was item number 2, right? The third thing is these alkalis: sodium, potassium, a little bit of calcium, and of course those come directly from our hydrated cement matrix. And the fourth and final thing is moisture. Now, if we don't have that moisture, the moisture is the most important part. The alkalis can be out here, over here. We still need that moisture to bring it over to the aggregate to cause that reaction. So what the fly ash will do is a few things. First and foremost, densify the capillaries of that hydrated cement matrix, hydrated cementitious matrix, to reduce pore connectivity, as well as pore connectivity, in turn densifying the hydrated cement matrix. And by doing so, we do 2 things. One, we arrest or reduce the ability for that moisture to migrate through reduction of permeability. And then 2, we also chemically bind that calcium or the soluble alkalis in the now hydrated phases, those calcium silicate hydrates that we get from pozzolanic reaction. Now Whitney said, she asked, do we get a increase in cement efficiency? And if we are getting pozzolanic reaction, it's a very clean pozzolan. Yes, there's a chance that we're going to get increase in cement efficiency, especially when we go out to the later ages. But because we don't have that moisture migration, we don't have that major pH sink. So this is the second thing. We don't have that cement pore solution changing that pH at the interface between the aggregate and the hydrated cement matrix, which normally causes that alkali silica reactivity because of those alkalis would migrate with that moisture. So what did we talk about so far? It's the densification within the body for moisture migration.
Right.
It is increasing the hydration kinetics. So you are consuming some of that water and causing a binding of the alkalis.
Chemical binding, right.
And then you are enhancing that interfacial zone either by producing more of that paste and chemically binding or doing something with that pore solution instead of it just being pore solution and acting in a bulk state. Now it's a hydrated phase, so everything's chemically bound at that, especially at that interface. You're also locking in that aggregate and creating a composite that's even stronger. Do I have to hold this anymore?
No, I think you're good.
Yeah, I think you're good. So I think those are 3 things that are good to hang your hat on. But I mean, if you take a deeper look into it, especially have like an RCA, which we can get into another one.
Sure.
You can do a pre-soak with your colloidal silica as well as use a fly ash. So to really do a whole holistic approach.
Could you use that regularly on reactive aggregate
Oh, totally.
as a way to?
Yeah, pre-soak it. Yeah, like especially in the summer when your construction is at its peak.
Right.
You can spin up the aggregate, throw it in there with
Right.
your headwater.
You just have crappy aggregate, and
Right.
that's how you
You
handle
can
it.
use like that Kremling aggregate.
Right.
Yeah, and Carly, I think you use the Kremling aggregate. Either it's not you, it might not be you, it might be one of your competitors up in Kremling, right by Silverthorne, or
Right.
right by.
Yeah.
Yeah, it's pretty reactive stuff. We were using 35% Class
Right.
F fly ash, and ended up going away from. I think they ended up going away from that Kremling aggregate.
Oh,
altogether.
probably. It was
Yeah.
incredibly reactive.
Pretty bad stuff out here, but worse in New Mexico,
Sure.
Texas, California. I think Oregon's got some pretty bad stuff. So, yeah, hopefully answered your question. Let us know if that helped out. Does that seem like that was answering the question? Yeah. Let us know if you got any other concrete questions, concrete concerns. Don't forget to like and subscribe. Ding that bell for notifications. Go concrete!
Beat asphalt.
Great asphalt.